Thank you very much. I'm very happy to say something about semi-structured log data for anomaly detection. I'm Marcin. I'm a data science team leader at F-Secure in Poznań office. I'm now almost 4 years working for that company in cybersecurity. I'm working as a data scientist, but before I was a backend developer, and I also had a career in the scientific world. I was a researcher. So I'm not only interested in data science, data analysis, but I'm also interested in bioinformatics. Maybe some of you know the company, but I will say a few words about it. We are probably the biggest cybersecurity company in Europe. We operate in many countries. We have almost 30 offices and 1,700 workers. And to summarize, I will say you something about the security and log data, and maybe give you a very short introduction to history of natural language processing. Then I will speak about word embeddings and give you a snapshot how to normalize or find rules for data normalization. And at the end, I will tell you something how to detect anomalies with that embeddings. So to give you a glimpse how our products try to find hackers already when they are operating in the organization, I will just show you a few slides. What is the pipeline how we gather data? So on in our organization, in a client, we have deployed sensors that sense logs, basically. So text data, we call them events, and they send it to our backend. In the backend, we have many different machine learning statistical analysis of that events, and we try to generate anomalies, and those anomalies are later viewed by our threat hunters. So we can have some degree of false positives, and human will confirm that something is very malicious, and we should inform our client about hacking activity. And we promise to give such information to our client within 30 minutes from the detection of such malicious activity. So what actually is semi-structured log data? In natural text, if you read books, I would call it unstructured because we have just flow of words. There is a semantic and syntactic meaning, but when we talk about logs, usually there is some kind of text. It can be either HTTP logs from Apache server that has some structure. It's like timestamp, there is maybe error or warning, and there is a message containing some information. So sometimes it has schema, but usually the schema can change. So we speak about text data, usually a JSON, and it's usually in the log context, it's a time sequence. And the schema can be flexible. Over time, there can be additional fields, additional meanings, different data types. They can be nested structures. They can be listed. So it's not as in SQL databases that you have a big table and you can say what is the schema at the beginning. We rather derive schema on the fly when the data arrives. And in the pipeline I just showed you, it's usually big volumes of data. We process millions and billions of events of such type. And in the further talk, I will usually just give you an example of process creation events. So we can say which process started which process. So we have parent process and child process, maybe path of that and the file name and SHA-1 and of the file and so on and so on. So out of these events, we could actually build a process tree to recover which process spawned which process. And we would like to find anomalies in such process tree, actually in the chains. So we believe that if there is anomaly in such a chain of execution, it might be some malicious activity. Anomaly doesn't mean a malicious, but we believe it's correlated. And something that usually people forget, this is a product that people, like organization pay, so we have some CPU, RAM, and latency restrictions. So we try to do this anomaly detection with restrictions of our resources. So we would like to have a more or less reasonable cost of that processing if you imagine that we process billions of events. Okay, so let's talk how we can do that anomaly detection. If we take a look on the history in NLP, at the beginning there was probably experts writing some handwritten rules. Later there were simple statistical models, maybe n-grams with more advanced machine learning. But later we have big advantage of recurrent neural networks, and especially long short-term memory cells and different architectures that allows natural language processing to develop quickly. So nowadays we have this new development that is transformer or attention, in other words, and we have very huge models trained of gigabytes of text and different architectures from top companies like Google or Facebook or other big companies. So they are massive, and probably that could be a good start to work with, but this is usually trained on natural language. So we cannot do this. We cannot take this for example, BERT model and do transfer learning because it's usually trained on English and we have log data. So we could start from the beginning, build a baseline model to compare it, because we would like to have, maybe simple model is good enough with the resources that we have. So with back of words approach, you usually take the event and then encode what kind of program is executed within this event. But in such a way, you can build either one-hot encoding, count vectors, or inverse the different way of counting the events. But anyway, you get huge matrix that is usually sparse. So you have huge feature vector with hundreds of thousands of columns, and then easily you get this curse of dimensionality problem. And there are other problems, like if you take just is the program in the event, usually you lose the order of the execution. And it's important is the explorer calling CMD or CMD calling explorer. Of course, you can use n-grams, but then this feature matrix is even bigger and even more sparse. And actually, this is not the biggest problem. The biggest problem is that similar programs of different versions of the same program will be different features in that matrix. So also in our context of machine learning in cybersecurity, the data patterns changes. There are updates of programs every day, Windows updates, new versions of programs, new companies coming to the product. Also, we are working in an agile way, so we develop our sensors. They send different data, different schema can be applied to our data. And just few shots how variable the data can be. For example, if there is a directory that contains a date, there is already like hundreds of versions of that. You can write date in many ways, so it's even more. Programs has versions, so usually like you can have version of .NET or database or Java, or you can just have a localization, so like PL directories or PL code in the name of the program. Even that's not the best, not the worst case. The worst case is actually that some programs has random components, or some directories has random components like UIDs or user IDs or temp directories, or installation is downloaded automatically, gets random digit at the end, or MSI gets some kind of hex middle in the name. So that creates a huge word imbalance. So you can imagine that you have path, root of the directory, like system32 is very common to many files, but then this with programs or directories that has this random component is just like single event in such a stream. So we try to use word embeddings to fight these problems, to find similar, to encode words into vectors that have some meaning of similarity. So first of all, we need to define what is a word actually in the log data. So in our case, when we talk about program, like new process events, we could, for example, split by slash and then have words as directories and file names or program names. And then for each of that words, we would like to assign to it not a 1 that means, or 0 that it exists or not, but we would like to assign a vector of floats or of real numbers to have the representation in some continuous kind of way. So we believe that each, let's say, column could represent some abstract meaning, like color, is it animal, is it machine, is it human, is it male or female, and so on and so on. And what is even more important, in natural language, there is assumption that the word meaning actually can be defined by the neighborhood context of the word. So if the word is in the same context, it probably means the same. So this is very good for our use case, that if we have a version of the program like Java directory, then if we have other version of that, it probably will have very similar neighborhood. And it, at the end, the embedding will create a very similar vector. So we use this concept to create the embeddings, but then because we have this random components that are huge and this huge imbalance of the words, we actually try to normalize our data set to lower down the memory usage or CPU usage. And we could actually use the initial embedding on subset of data because it's very good to find like if something is random, it will be many times on many machines visible. But then in the final embedding, we could use those normalization rules on the whole set and then train the final model on the whole set so that we will, at the end, push it through the anomaly detection engine. Okay, so we need to create neighborhood or the sentence in natural language because the sentence definition actually forces what is similar and what is not similar. So in our case, there are many options, but for one option is that, for example, we take just a path of the child process, then the file name of the process of child process, and then, for example, parent file name. So we would like to have, okay, we believe that if the programs are stored in the same localization, then they are similar, but they are also similar if they are executed by similar, same parent process. And you can see that there are many examples with that kind of, I call them pathological random parts. So they can be either the version of some parts of the word as random. That can be UUID or I don't know, Firefox version and so on. So platform. And we tried different word embeddings, but we found out that the fast text is slightly better than word to vec. This is because it also takes into account the n-grams of characters of the words. So we took for the project we took a sample of 22 million roll events, and then we created such sentences that I described. It was more than 500,000, but you can see that this actually has, like, almost every sentence has some random kind of path because there is about 500,000 of unique words in that vocabulary. Okay, but it actually worked. So Python is similar to different Python versions, or JDK is similar to different JDK folders with different versions. Of course, similarity can change, but more or less it is able to cluster the data in the desired manner. So we then look on the clusters. We do the dbScan clustering and project it with tsni. So you can see the big clusters of some temp directories or the MSI, as I already showed you, some Java underscore digits, UIDs, and so on. So we then try to generate normalization rules or regex rules to just minimize the vocabulary size. And as I already told you, we did the dbScan with cosine distance and then try to find patterns. And this is rather trivial approach. For each cluster, we group the words by the length. Then for each group, we try to detect the conserved part of the letters, of characters, and then for the rest, we try to find a pattern. So for example, here is hexadecimal kind of options, so we can create easily the regex rule that there is MSI, 3 hexes, .tmp, and so on, or 4 hexes. And that are other examples of the rules, so of temp directories or program names. But for example, this one on the right bottom is pretty funny. It is very general. It actually matches all the programs that has 8 characters, .3 characters. So we had to curate this list manually, so that very general rules are not applied to the at the end. Okay, so we normalized the vocabulary, and we were able, with about 30 rules, to squeeze the vocabulary 7 times. So now it's about 75,000 of unique words and 1,700,000 unique sentences. So I think it's beneficial to do that in our context. Okay, let's come back to the initial program. We wanted to find the anomalies in process creation chains. So, for example, let's say PowerShell called PowerShell could be anomaly in the context of like CMD and wget and explore. So how to find such anomalies? There are many different ways, but we tried autoencoder model. So it's like it is very similar to compression. So we try to compress some set of values into smaller set and then decompress it. So it's more or less like loosely compression. So when you put let's say, representation of the words or vectors represented that represent such words, we would like to recover that vector. And if there is, let's say, random unseen combination of words, the reconstruction error at the end would be big, so that you will get something wrong, basically. So we believe that for the assumption for autoencoder is that we would like to overfit so that it will learn the patterns that were in the training set, but when you pass new data that was never seen, the reconstruction error should be big. And we actually applied it to LST recurrent autoencoder, and we use GRU cells because they are just a little bit faster. So we had 3 levels for encoder and 3 layers for decoder. And actually, this is basically proof of concept that it works. So for the training set, the reconstruction error is below 0.004 in our case, so it's this blue class. But when we randomly shifted all the words in such a sequence of process creation chains, the reconstruction error was high. So we actually proven that this autoencoder could be used as some kind of anomaly detection. So in practice, in production, we probably would put a threshold at the end of this region here, so that such points would be investigated by our threat hunters and maybe with additional information from other events, it will be enough to justify if there was some malicious activity. Okay, so to sum up, I have told you something about the word embeddings for the log that we process. I showed you a simple way to generate rules based on clustering, and then at the end I showed you some concept how to use autoencoder to find anomalies in such space. And I would like to thank my team, especially Michael, Bartosz, and Paweł that did the research and the project, and other team members for supporting us. And if you are more interested in NLP and cybersecurity, I encourage you to go to Zuzana talk tomorrow at 12. Okay, so if there are any questions, I'm happy to answer.
When you train the autoencoder, how important is it to clean the data first from these anomalies so the autoencoder wouldn't learn them? Or is the anomalies so rare that they do not interrupt?
Yeah, that's, I don't know actually, but we believe that in this cybersecurity context, the hacker activities doesn't happen often. So it's like 1 to million. Probably it's fine to have one point that is up. So like this point could be malicious, but it could be just accident of this autoencoder kind of couldn't learn such pattern. So it's we just put all the data we had, and the assumption is that of course there will be some kind of malicious or anomalous points there, but they just the imbalance is so huge that we didn't care.
Okay, thank you.
Hi, very nice talk. Have you thought about visualization of explanation of anomaly? Because you said in your workflow that each anomaly is inspected by some operator. So do they receive any help from the model that justify the score?
So from the model, probably not, but this is a small piece of the bigger system. So it's, let's say, one enrichment, and we say, okay, this is anomaly because there is an uncommon process chain, more or less. And then they can focus, okay, then what was the path of the execution, and try to check, okay, what this process actually did, and then they can investigate more. And of course, there are other events, so they can get also alarms from I don't know, maybe somebody saved the file that is in the unusual path, or they created some registry rights that are not typical for such a program, and so on. So they will have more information to put bigger picture.
Thank you very much, Dan.